Human beings are about to enter into a new and unexpected frontier in space: asteroids.
Asteroids hold the answers to many of the secrets that can help us to understand our own planet.
These small rocky worlds could offer new opportunities, such as the ability to mine their resources or to use them as pit stops for future space exploration. However, they also pose a danger to the Earth that could eventually cause a planetary catastrophe, like the one that wiped out the dinosaurs.
There was a 10-kilometer asteroid 60 million years ago that hit Earth. Presumably we could have another asteroid impact like that at some point in time in the future.
We are now starting to prepare for that unlikely event by tracking the closest asteroids that could threaten our survival as a species. But there is still much to be done.
Right now, NASA has several ground-based surveys that use telescopes to scan the sky and look for threatening asteroids. They're trying to find all the asteroids that might present a threat to the Earth in the future.
Asteroids could also help us solve great enigmas about the origin of the solar system and how the planets were formed. We still don't know if they played a key role in delivering elements of life to Earth.
Asteroid Bennu is an interesting asteroid. It's the type of asteroids that could have brought life to Earth in its early days of formation.
Several missions from NASA, ESA, the European Space Agency, and JAXA, the Japan Aerospace Exploration Agency, have recently studied some of these mysterious celestial bodies and have made amazing discoveries.
The Lucy mission is going to be the first mission ever to explore the Jupiter Trojans. And we are going to actually get a close-up view of 6 different Trojans in this one mission.
In the near future, asteroids could become potential resource targets, which might kick off a new gold rush in space.
From our perspective today, that's a limitless source of resources out there in space. And so there's a lot of money to be made out there in space.
In the coming decades, we will witness a total revolution of the space industry. The exploration and future mining of asteroids will undoubtedly open up totally new possibilities. After more than 2 years of travel, on December 3, 2018, the OSIRIS-REx probe finally reached its target, the asteroid Bennu.
Asteroid Bennu is a carbonaceous type asteroid, so that means it's predominantly made of carbon, much like we are here on Earth and what primarily Earth is made up of.
The culmination of this NASA mission's adventure will occur when the spacecraft sampling arm touches the surface of Bennu, collects some asteroidal material, and brings that sample back to Earth. This tiny sample will allow us to answer big questions, like where we come from and what is our destiny. Bennu hides secrets about the history of the Sun and planets, as well as the origin of life, since it, like all asteroids, is the leftover debris from the solar system's formation process.
Asteroid Bennu is an interesting asteroid to study for a number of reasons. It's the first carbonaceous type asteroid that we've gone out to collect the sample from, and carbon type asteroids are the type of asteroids that could have brought life to Earth in its early days of formation.
Bennu is just one of the hundreds of thousands of asteroids that float in the space in our solar system. These tiny rocky worlds are irregularly shaped, though a few are nearly spherical, and they are often pitted or cratered.
So most asteroids are located in a belt between Mars and Jupiter that we call the asteroid belt.
However, there are more asteroids in other locations. The so-called Trojans are asteroids that share an orbit with a larger planet, but do not collide with it.
Trojans are just objects that happen to be at what we call a Lagrange point of a planet. The Lagrange point is 60 degrees before or after. And the way to think about it is that if you take a planet and the sun, the gravitational force of an object at exactly 60 degrees between those two objects, plus the centrifugal force of rotation, all cancel out. So if you put something at that 60-degree point, it'll stay there forever. And so these Trojans, therefore, are leftovers of the formation of the planets. And that's what makes them so interesting, is that they're an ancient population that shared an orbit with Jupiter.
The main population of Trojan asteroids are the Jupiter Trojans, which is thought to have as many asteroids as those in the asteroid belt. There are also Mars and Neptune Trojans. However, they are not as numerous as the Jupiter ones. The other major population of asteroids is the near-Earth asteroids.
There's also near-Earth asteroids, and these are asteroids that cross the orbit of Earth. So they're ones that could potentially hit Earth.
The near-Earth asteroid population is about 1,000 times less populous than the asteroid belt. The main asteroid belt has about 1 million objects larger than about 1 kilometer, and the near-Earth object population has about 1,000 objects larger than 1 kilometer.
However, not all asteroids that float around our solar system belong to one of these populations, near-Earth asteroids or Trojans, or are trapped in the main asteroid belt. There are rare exceptions. On October 18, 2017, an unexpected discovery shocked the international scientific community. Astronomers discovered that a very weird asteroid passed by the Earth.
This asteroid seems to be at least 3 times as long as it is wide. It is possibly as much as maybe 8, 9, or 10 times as long as it is wide. This is something we have yet to see in our solar system, and how it gets produced is something we're not sure how to do this at this point.
The object was initially thought to come from the Oort cloud, a region far outside the solar system, which can have extreme orbits that take them careening through the inner solar system at speeds exceeding 37 miles per second. This strange celestial body was so significant because it moved at the astounding speed of 54 miles a second, too high to have come from our solar system. The conclusion was clear. It had to have originated from another solar system, making it the first ever discovery of an interstellar object. They named it Oumuamua, which means something like first distant messenger in Hawaiian.
Oumuamua is the first interstellar asteroid we've ever seen. So this is an asteroid that came from another solar system. And it came and it passed through our solar system and is on its way out of our solar system. And that's really amazing because we live at a unique time when our telescopes have gotten better and we're scanning the skies regularly and we're able to detect this first interstellar asteroid. It is likely that other objects have passed through our solar system and we just never were aware of it.
Perhaps it is a messenger from another star system, but what can it really tell us about where it came from? Since it was moving so quickly, the time available to study it was extremely short. As a result, soon after its discovery on October 24th, a wild race began between astronomers from all around the globe to obtain telescope data and unveil its secrets. We were able to analyze Oumuamua's chemical composition using photometric colors and spectra that revealed that it has a reddish color and might have come from the inner part of its original star system. However, The great mystery surrounding this interstellar object was its extraordinary speed of 54 miles per second, much higher than any other object from our solar system.
That object had anomalously large non-gravitational forces. So that was a little unusual. With comets, when you see non-gravitational forces, you tend to see dust produced because the gas is escaping and it lifts the dust off the surface. The interesting thing about this object is we didn't see any dust. So the question is, how can you get gas escaping and not produce dust? And that's telling us something that this object is unusual, at least compared to objects that are made in our solar system. And that's sort of a mystery.
Although we don't know Oumuamua's exact composition yet, we know the composition of asteroids that have been observed and studied for decades. Most asteroids fall into the following three categories: C-type, S-type, and M-type. C-type, or carbonaceous asteroids, also known as chondrite asteroids, are the most common. Their composition is believed to be similar to that of the Sun, although they lack hydrogen, helium, and other volatile compounds. They are dark in appearance, and they are among the most ancient objects in the solar system. S-types, or stony asteroids, are made up of silicate materials and nickel iron. They account for approximately 17% of all asteroids, and they are the second most common.
One is one we call S-type. These are often ones that were referred to as more stony type objects, and we think are very similar to a type of meteorite that's very common that lands on the Earth called ordinary chondrites.
M-type asteroids are metallic and much brighter than C-type asteroids. They are made of nickel, iron, iridium, platinum, gold, or other precious metals, either pure or mixed with different amounts of stone.
M-type asteroids are very unusual. Some of them may actually be metal. They may actually be produced in the interiors of asteroids. The core materials managed to escape the asteroid, probably in some gigantic collision. Other M-types, though, may be different compositions altogether, and there's still a great uncertainty about exactly what all of the M-type asteroids are.
If we want to study the composition of an asteroid, one of the best ways to do so is to analyze meteorites at an automated mineralogy lab, since many of them come from asteroids. The team at the Mineralogy Lab of the Geology and Geological Engineering Department at the Colorado School of Mines can examine the compounds of any meteorite sample with extreme precision.
All meteorites are fragments of rocky or metallic matter that's been transported from objects out in the solar system, and they've landed on the Earth's surface. And we can collect them and study them in the laboratory and work out their chemical composition, which minerals they contain, and therefore we can extrapolate the resource potential of particular bodies that exist elsewhere in the solar system.
Our automated mineralogy system is SEM-based, so we're using a scanning electron microscope to basically scan our sample. We have to prepare the sample. It is really important that our samples have a perfectly flat surface. So we have to polish our samples down to 1 micron. So the surface is perfectly even, so when we have the beam interact with the sample, we don't have other interaction features that will change the result of our interaction. We have our electron beam interact with the sample, and then we investigate basically the interaction product we get from the beam interacting with the sample. The result from this interaction we compare with the lookup table, where we have definitions for all minerals and phases that are of interest to us. And then our software program, the automated mineralogy software, will produce a false color map based on the definitions written and based on how it compares the analytical data with our lookup table.
Therefore, we can determine if the sample has more or less iron, nickel, platinum, or more or less of any other mineral. All asteroids, no matter their composition, are rocky remnants left over from the early formation of our solar system about 4.6 billion years ago. So they offer us clues to unveil the most hidden secrets of our most remote past. We've been exploring and studying asteroids for decades to understand what happened before us, before life on Earth, and even before Earth itself. Asteroids, considered floating fossils, can help us trace the solar system's evolution from a primordial disk of dust and grains. Asteroids can help us understand how the planets were formed and the origin of life on Earth, since there are theories that claim that the massive impact of asteroids was mainly responsible for delivering elements of life to primitive Earth. Asteroids are not just remnants of the remote past. They are also real hazards to Earth. Some pass close by Earth and could hit our planet one day, as occurred in the past when one ended the reign of the dinosaurs.
There was a 10-kilometer asteroid 60 million years ago that hit Earth. That's one of the current stories about the dinosaur ending event. Presumably we could have another asteroid impact like that at some point in time in the future, although right now it's not showing up as likely. We haven't found it yet.
A few years ago we saw an object the size of a large office building impact over Chelyabinsk, Russia. Very much smaller scale event, but still, in some ways, devastating for that particular city.
Scientists continuously monitor Earth-crossing asteroids whose paths intersect Earth's orbit, and near-Earth asteroids that approach Earth's orbital distance to within about 28 million miles and may pose an impact danger.
The question is what to do about this. So right now, NASA has several ground-based surveys that use telescopes to scan the sky and look for threatening asteroids. They're trying to find all the asteroids that might present a threat to the Earth in the future. So far we've had some success with this, where we think we've found all of the 1-kilometer asteroids and larger bodies that can hit the Earth. But as we go to smaller worlds, we go to, let's say, worlds that are half a kilometer or 100 meters or so, these objects are still threatening. We're still working to find some of these bodies.
Bennu, the target of the OSIRIS-REx mission, is one of the most potentially hazardous asteroids to Earth that is currently known, even though its odds of colliding with Earth are still relatively small.
NASA hasn't been able to control or change the trajectory of any asteroids yet. We are really at the beginning of understanding the types of asteroids that could impact Earth and how we might redirect them, which is one of the goals of the OSIRIS-REx mission, is to understand how the asteroid Bennu actually orbits and what we might do in the future to redirect it.
In fact, there is a NASA mission, the DART mission, that will test a technique for defending the planet from a future hypothetical asteroid impact, the main goal of which is to attempt to change the trajectory of an asteroid. Currently, there is no coordinated international plan to act in the event a potential hazardous asteroid is detected. Nevertheless, there are several non-governmental organizations that are focused on this issue. One of the most active is the B612 Foundation, which works toward protecting the Earth from asteroid impacts and informing and forwarding worldwide decision-making on planetary defense issues.
There are a number of groups worldwide that are concerned with asteroid detection and defense. and one of them is the B612 Foundation.
The B612 Foundation works to make interpretation of asteroid data open and accessible, and serves as an informed source for an international community of policymakers and scientists who can best help to achieve these goals. We haven't had any of these extinction-level events in recent history, but there might be one in the future if we don't do something about it. Some of Earth's largest craters, which are millions of years old, are large enough to hold a big city or even a small country. One of the most stunning craters that was recently discovered was in a remote area of northwest Greenland, buried under 0.6 miles of ice. It's 1,000 feet deep and 19 miles in diameter, which is bigger than Paris. That crater formed less than 3 million years ago, when a meteorite more than half a mile wide smashed into that area. The devastation that an impact like that could cause today would be catastrophic. Over the last decade, governments have started to gain awareness of this threat and have begun to make progress on the planetary defense front. With the ground-based U.S. National Science Foundation's Large Synoptic Survey Telescope, the LSST, 5 years from entering service, and with the selection of the Space Telescope NEOCAM as a finalist in the NASA Discovery Mission Program, scientists will be able to track 90% of near-Earth asteroids larger than 460 feet in about a decade.
We have to do something, or one day we will not be around anymore to ponder the asteroid problem. The asteroid problem will have done away with us.
Asteroids are among the oldest celestial bodies in the solar system. As floating fossils that witnessed Earth's primordial stages, they convey key information about the origin of life, as they are believed to have delivered the elements of life to Earth during its early stages.
Asteroids are fascinating celestial bodies that are somehow misunderstood. Asteroids hold the answers to many of the secrets that can help us to understand our own planet.
In addition to asteroids, comets and other small bodies offer clues that can help us understand Earth. Comets are very similar to asteroids. Both are remnants of the very distant past, like flying fossils from the origin of the solar system. However, while asteroids consist of metals and rocky material, comets are made up of ice, dust, rocky materials, and organic compounds.
A comet is an object that shows activity, and asteroids generally don't, although there are rare occasions of asteroids that show activity as well. The comets typically have a very eccentric orbit. So when it comes closer to the sunlight warms the gases and ices in the comet and creates a gas and dust tail.
2 missions targeting comets have helped us to unveil some of their secrets. NASA's Deep Impact mission and ESA's Rosetta mission, one of the most important missions led by the European Space Agency. In 2005, some of our ideas about the formation of comets and their role in delivering the elements of life to Earth changed thanks to NASA's Deep Impact mission, which was a pioneer in the study of these mysterious and beautiful celestial bodies. The probe reached the comet Tempel 1 on July 3, 2005, and the following day it successfully released an impactor on the surface of the comet, which generated a brilliant flash of light, later discovered to be ice and dust debris ejecting from the fresh impact crater. The Deep Impact mission was the first attempt to peer beneath the surface of a comet. It revealed a number of new findings about comets and their composition, including evidence of water ice and organic materials.
The Deep Impact mission was a wonderful example of the kinds of technology that we want to have available to us in the future for deflecting the trajectory of a potentially hazardous object. Deep Impact was purposely targeted to impact the nucleus of Comet Tempel 1, not for the purpose of pushing it off course, but for the purpose of studying what the subsurface properties of that comet are like. The side benefit, of course, was this is the first time we'd ever done something like this, purposely targeting a spacecraft to slam into a small object in the near-Earth environment. And so it was a great accidental practice, if you will. It was an unintentional practice of the kinetic impact method of deflecting asteroids.
However, we had to wait almost a decade until the next mission to a comet to discover more about these mysterious celestial bodies. It was ESA's Rosetta mission, a spacecraft sent to the 67P Churyumov-Gerasimenko comet by the European Space Agency, that gave us new evidences about comets. On November 12, 2014, an unbelievable milestone was reached when it successfully deployed its Philae probe on the comet's surface. The first time in history that such an extraordinary feat was achieved. Rosetta gathered significant data on the comet. It revealed that it had a remarkable array of surface features and many processes which contributed to its activity, painting a complex picture of its evolution.
Coming in with the Rosetta mission, one of the strong motivation was whether or not comets played a role in delivering water to the Earth or potentially even organic compounds. I believe some of the outcomes from the Rosetta mission are now clearly showing that the comet didn't really play much of a role in delivering water to the Earth. We can look at isotopes of hydrogen, for instance, and deuterium on the comet, and they have distinct properties to what we find on water on Earth. And so there doesn't seem to be much room for delivery of water from comets. So that is an important aspect. Regarding the organic material, this is still an ongoing debate. Clearly, comets contain lots of organics, and so in principle, there is an opportunity to deliver organic material to the surface of the Earth, but it's totally unclear whether or not they actually played any significant role in the, let's say, formation of complex organics on Earth that eventually led to the formation of life.
The main shocking conclusion after all the data gathered was analyzed was that comets didn't bring water to Earth. Regarding asteroids, there are theories that suggest that they might have planted the ingredients for life on Earth. The key point would be to know how much water they have, which would be considered evidence of how they helped plant the seeds of life on Earth. There are two ongoing missions that may provide an answer to this question. The Japanese Hayabusa 2 mission to the asteroid Ryugu, and NASA's OSIRIS-REx mission to the asteroid Bennu. Both missions will collect asteroidal materials and bring them back to Earth for in-depth analysis.
The OSIRIS-REx mission to asteroid Bennu is a sample return mission to detect amino acids on an asteroid and bring back a pristine sample to Earth for study here.
We will learn a lot from comparing the two asteroids, Bennu and Ryugu, and understand the similarities and differences between their samples. The first one to be launched was JAXA's Hayabusa 2 mission, a mission of the Japanese Aerospace Exploration Agency that left Earth in December 2014.
A Hayabusa 2 mission is visiting an asteroid called Ryugu. It's about 1 kilometer across. It also seems to be a primitive carbonaceous chondrite. But the interesting question is, did it come from a different parent than, let's say, Bennu? It's possible that both of these asteroids came from very different parent bodies originally in the asteroid belt, but it's also possible they came from the same parent body. In the process, we're going to learn about the nature of very large asteroids that are primitive in the asteroid belt.
It successfully reached Rugo on June 27, 2018. It landed 3 hopping rovers on the surface of the asteroid. Some of these rovers have already sent home stunning images. However, the climax of the mission came on February 22, 2019. That day, the spacecraft was able to make the most complicated maneuver, the first touchdown. The probe was able to grab a tiny sample of dirt off the surface of the asteroid. It was the second time that humanity has ever achieved such a feat. These are the actual images of the historic moment of the first touchdown. Hayabusa 2 is hoping to bring back to Earth between 10 to 100 milligrams of material for in-depth analysis. The goal is to clarify the origin of life by analyzing samples acquired from a primordial celestial body, such as a C-type asteroid, to study organic matter and water in the solar system, and how they coexist while affecting each other. The other asteroid sampling mission that is now underway is NASA's OSIRIS-REx mission. On December 3, 2018, after a 1.2 billion mile journey, it reached its asteroid target, Bennu, and started to orbit. It is scheduled to bring back a sample of this mysterious celestial body to Earth in a sample return capsule in 2023.
The OSIRIS-REx mission launched in September of 2016, and it's a 7-year mission to go out to the asteroid. So we're going to reach the asteroid in 2018 and perform science studies of it through 2019 and 2020. And then in 2021, we will begin our return back to Earth.
The OSIRIS-REx mission will answer some key questions about the origin of the solar system, since, as an asteroid, Bennu is a flying fossil from our solar system's most remote past, and about the origin of life on Earth, since, as a carbonaceous asteroid, it may contain molecular precursors to the origin of life and Earth's oceans.
One of the reasons why we want to find out whether or not there are amino acids on Bennu is because we're not exactly certain how the building blocks of life got on Earth in the first place. One of the theories is that asteroids may have impacted Earth while it was in its early formations, and if those asteroids had amino acids on it, then it would have seeded life here on Earth.
OSIRIS-REx will determine Bennu's physical and chemical properties, which will be critical information to have in the event of an impact mitigation mission. It is scheduled to touch down on the asteroid's surface with the touch-and-go sample acquisition mechanism, or TAGSAM, that consists of a robotic arm with an attached sampler head.
We use the TAGSAM arm, which is kind of like a really expensive vacuum cleaner, which reaches out and touches the surface of Bennu from about 6 feet away and uses nitrogen to stir up the dust and the regolith that's on the surface of the asteroid. And that gets collected inside of a round collection plate, which we then store on side of the spacecraft and bring back to Earth.
From the most distant asteroids orbiting beyond Jupiter to near-Earth objects, each space rock contains clues to trace the epic events that shaped our solar system as we know it today. By studying these small bodies, we can learn more about how they accreted to form larger planets and about the time period when they massively impacted primitive Earth's surface. Everything started with a primordial disk comprised of grains of dust, which were tiny particles of rock, metal, and ice swirling around our primitive sun. Asteroids can help us investigate how the planets were formed from the progressive accumulation of smaller objects.
Well, an asteroid is sort of a leftover piece of the original building blocks which made the planets. Okay, originally we think our solar system was mainly made up of gas and dust. And slowly the dust began to form in larger and larger objects and became objects very similar to the asteroids we have today. Continued to grow, and ultimately they became into planets, they became into large objects in general. But some of the smaller objects that didn't manage to get into the planets became sort of the leftovers, and they're what we know today as asteroids. So these bodies have changed very little since the earliest times in solar system history, about 4.5 billion years ago.
Asteroids can help us investigate how the planets were formed from the progressive accumulation of smaller objects. Two of the most peculiar celestial bodies that may help us understand how the planets were formed are Vesta and Ceres. They are the largest bodies in the main asteroid belt, two protoplanets that never grew enough to become planets. NASA's Dawn spacecraft, which recently ended its mission, orbited both and definitely demonstrated that they are quite different from regular asteroids.
The Dawn mission is a NASA mission that was taught to investigate with great details the main objects in the asteroid belt. The targets were the asteroid Vesta and the dwarf planet Ceres, which are the most massive object in the asteroid belt in between the orbit of Jupiter and Mars. The name of the mission tells already what the mission is about. Dawn means, really try to understand the origin of the solar system, how the solar system was formed. And these objects, the targets of the missions, were considered and are still considered to be objects that formed very early on in the solar systems.
We almost call these dwarf planets. One is called Ceres, which is over 900 kilometers across. The second one is called Vesta, which is over 500 kilometers across. These two asteroids have very different compositions and a very different nature.
On November 1st, 2018, Dawn ended its mission. Currently, it's in orbit around Ceres, where it will remain for decades. Dawn found that while many asteroids are loose collections of rubble, the interiors of Vesta and Ceres are layered with the densest materials at their cores.
The asteroid Vesta seems to almost be like a little version of a planet that formed in the inner solar system. We believe it got so hot that it melted at one point, forming a core. It actually has material on the surface that makes it look like it's actually gone through volcanism, where basaltic material has come out and flowed across the surface of the rest. We actually believe we have some kinds of meteorites that actually came from this asteroid Vesta. And so we've been investigating that world to try to see the differences between what we could see from a spacecraft mission and what we can see from the samples that arrived on the Earth.
It's fascinating to think that we have a chance to directly study a piece of Vesta here on Earth. Thanks to some meteorite samples, the team of the Mineralogy Lab of the Geology and Geological Engineering Department at the Colorado School of Mines can investigate the main compounds of the surface of the protoplanet.
This one is a howardite, so it's an impact progression. And these are little bits of rock on the surface of Vesta that were smashed up during other asteroid impacts. And these bits of rocks were thrown about the surface, accreted together. They were fused together by the regolith, and then a later meteorite impact has thrown this piece off Vesta's surface, and it's impacted the Earth. This sample here is a diagenite. So this is like a gabbro that we would find on Earth, and this forms at some level within the crust, and it's an igneous rock. So it crystallized from a magma at some point in time. And if we can study the chemical compositions and the proportions of the minerals that exist in.
The results from the analysis of these samples will give us their precise composition.
In the samples we have for this meteorite, you can find pyroxene, anorthite, you can find some apatite, some spinel, some quartz, of course, and those types of minerals. So the brighter the spot, the more iron content there is. So you see these gray areas have some iron content, but the most iron content is in these white spots, pixels here. So there's a good majority of this meteorite that actually has iron, but there's more concentrated spots throughout it.
The Dawn mission also studied Sirius, the biggest object in the main asteroid belt, revealing that it was an icy ocean world where water and ammonia reacted with silicate rocks.
Sirius, instead, is an entirely different object. It's a much higher content of volatiles, potentially also including some water. On Sirius, we find, for instance, minerals that are the results of what we call aqueous alteration. That simply means when you have rock interacting with water, you can form deposits, for instance, like carbonates. These are common things that we find on Earth. Sirius and Vesta are considered remnants from the early solar system. By studying these objects, we can really try to understand the details of the early formation of the solar system. This object, along with many other asteroids that are found between Mars and Jupiter, didn't have an opportunity to grow to larger sizes, like a full-blown planet like Mars or the Earth. And there are several reasons why this happened. We think the main reason is because Jupiter, which was a massive planet, is not far from this region of the solar system. Jupiter has enough perturbation to those little planetesimal small planets that were trying to accrete in order to form a much larger object.
Thanks to several pioneering missions to certain asteroids, we have been able to learn more about the origin of our solar system, about the role asteroids played as the building blocks of planets and in delivering the elements of life. Nonetheless, some unsolved mysteries remain. One of these mysteries is what is at the core of large planets. Although we can indirectly study the deep interiors of planets for clues about their origins, it's impossible to drill down into the core of any sizable object in space, including Earth. Nevertheless, a rare object called Psyche may offer the opportunity to explore a planet-like body's core without any digging. The asteroid Psyche appears to be the exposed iron-nickel core of a protoplanet, a small world that formed early in our solar system's history but never reached planetary size. Like Vesta and Sirius, Psyche's path to planethood was disrupted. There's an upcoming mission to this unique and strange asteroid that will help tell the story of planet formation by conducting an in-depth study of this metal object. NASA's Psyche mission. The mission is scheduled to launch in 2022 and will reach its target after a 3.5-year journey in 2026. It will help us to understand a previously unexplored building block of planet formation, iron cores.
We've never actually had a chance to visit a world that's made out of iron, which may be a metal world. We think the way you would get metal worlds is possibly they are the cores that have been extracted from a larger, probably asteroid, or maybe even a small mini planet that was blown apart by some gigantic collision very long ago. So this is our opportunity to see what cores of worlds may be like. But there's also this interesting question about what should geology be like on an iron world.
The history of the solar system is written in cataclysmic events that began in the early stages of the primordial nebula, that became the primordial disk of grains of dust. Giant collisions between bodies were central to its evolution. The position of the planets has shifted due to huge gravitational interactions, and these planet migrations are thought to have played a key role in the solar system's early evolution. The Trojans, as ancient remnants of that remote past that are trapped in the orbit of some planets, could help us understand what happened. In fact, Jupiter's Trojans could give us clues about what happened the last time Jupiter moved and about what role it played in the organization of the planets of the solar system.
Lucy is going to visit 6 what we call Trojan asteroids, which are these asteroids that lead or follow Jupiter in its orbit. One of the surprising things about the Trojan asteroids is that although they occupy a very small region of space, just this little region near Jupiter's orbit, they're physically very different from one another. Is that they formed at very different locations in the disk, and the gravitational evolution of the planets led to a large number of objects from that outer region being trapped in this little region.
NASA's upcoming Lucy mission, scheduled to launch in October 2021, will explore Trojans for the first time ever.
We're going to be visiting objects in both swarms. The whole idea of this is to understand the diversity of these Trojan asteroids, what makes them different, because that's going to be a key to understanding how our solar system formed. This is named after the discovery of the Lucy fossil. The Lucy mission is named after the hominid fossil, the Australopithecus fossil, Lucy, that was discovered in the 1970s. Just like the Lucy fossil revolutionized our understanding of hominid development, the Lucy mission will revolutionize our understanding of solar system formation and evolution.
Lucy's discoveries will give us new insights into the origins of our Earth and ourselves. Asteroids don't just make it possible for us to learn about the evolution of the solar system or the formation of the planets. They also offer us almost unlimited resources. They contain natural resources such as water, organics, and precious metals. In the near future, these asteroids may fuel the exploration of the solar system by robotic and manned spacecraft. They could become useful pit stops or stepping stones en route to more distant destinations like Mars or beyond. There are no gas stations in space yet, but scientists and engineers are already starting to think about how asteroids could one day serve as refueling stations for spacecraft on the way to faraway space destinations. These small worlds might also help astronauts restock their supplies of water or other materials. Asteroids are not just small celestial objects, but extremely small worlds that can help us understand our own world, Earth, as well as the solar system. They can offer us clues about its origin, its evolution, the formation of the planets, and even about the origin of life. Current technology allows us to dream of a not-so-distant future where asteroids will be pit stops for deep space exploration, as well as sources for mining metals, minerals, and propellant to be used in space and maybe on Earth. This is only the beginning of the adventure. The exploration of asteroids has just begun. Asteroids are no longer just small rocky worlds floating in space. They have become new economic opportunities and places strategic to space exploration.
There's almost unlimited resources in the asteroids. There are many different types, and they each contain different resources that we could use.
Most of them are made of metals like iron, nickel, or precious metals like gold or platinum that are very valuable. However, the most valuable material on asteroids is the simplest element, water. In the near future, we could use asteroids as pit stops to refuel spacecrafts en route to deep space with propellant made out of water.
That is where the value of asteroids really lie, as they become gas stations or pit stops or stepping stones in our process to explore further and further into the solar system.
In the last few years, space has become of interest not just to the public sector, led by national space agencies, but also to the private sector, resulting in an unprecedented industrial revolution. Several companies have plans to explore and use resources from asteroids. Most of these companies are based in the USA. However, there is a small country in the center of Europe that is playing a key role in this emerging sector: Luxembourg.
Luxembourg have become very interested in asteroid mining. They're bigger in space than they are on the ground.
But to make asteroid mining economically feasible, we need to solve some technical challenges.
The cost of sending a spacecraft to the asteroid belt used to be about the same as if the spacecraft were made of pure platinum.
Once those challenges have been overcome, we might start to dream of asteroids as our new targets, small, isolated worlds that could play a key role in future space economy.
I think there's a great analogy to the 1800s gold rush in the western United States for the economy of the future for the late 21st century out there in space.
You're looking for stuff that you want, and specifically, if you're going to turn an asteroid into a place for people to live.
We are about to be witness to a whole space industrial revolution that will see asteroids become our next frontier. In the last few years, several missions to asteroids have shown us that they have many resources that could be useful to us.
The advantages of asteroids are that they have a lot more favorable chemistry. The components that the asteroids are made of are a lot more of the things that we find valuable.
There is one type of asteroid, the C-type, also known as the carbonaceous or chondrite asteroids, that are the most abundant and have not just hydrocarbons, but also a key element for the future space industry: water. Water is an extremely valuable resource for several reasons. It will be necessary for resupplying. Astronauts could use asteroids as stops to refill the water tanks of spacecrafts in long, deep space journeys to destinations like Mars.
By having water on practically everywhere around the solar system, because there's millions of these asteroids floating around, you have the possibility to use water not just for humans. It's good for drinking. Water can be used to obtain oxygen. You can use them to shield you from radiation, to grow plants, whatever you need. But the real importance of water on asteroids is because you can use them as a means of energy, as a propellant.
You can just heat the water to steam and then use that as a rocket, a steam rocket. And that's a way to get around space. But another way is to take the water and split it by electrolysis into hydrogen and oxygen, and then use that in a liquid hydrogen, liquid oxygen rocket. And that's the most powerful chemical rocket we have today.
So in a way, water becomes, as we say, the oil of space. Because once you have that propellant that will help you to move around the solar system, get you to much further destinations. You will be able to now refuel, so you don't have to bring that fuel from Earth. And so that allows you to have larger rockets, larger payloads, and truly they become stepping stones, or sometimes they call it pit stops along the way.
Several missions have recently explored or are exploring several C-type asteroids, as the Hayabusa 1 mission from JAXA, the Japanese Aerospace Exploration Agency, or 2 ongoing missions, NASA's OSIRIS-REx mission and JAXA's Hayabusa 2. All of these missions have the peculiarity of being sample return missions, which means that probes will grab some asteroidal material and will return it to the Earth for its later analysis. These samples will be extremely useful to know much more about the real composition of asteroids and will allow us to study their real potential as resources. There's another type of asteroid, the M-types, or metallic, which are made of nickel, iron, iridium, platinum, gold, or other precious metals, either pure or mixed in different proportions with stone. Those asteroids might be used as an endless resource of materials and minerals.
They also are important because some of those asteroids, the metallic types, hold important metals that are used for a variety of things, for construction, like iron and nickel, and also the valuable platinum group metals. So once you have those metals, now you have the material that you need to develop manufacturing things like, for example, tools or spare parts, or even large construction material for satellites.
There are even some asteroids like Psyche, which are made almost entirely of metal that could eventually become very interesting targets for the future asteroid mining industry, as the metals are on the surface and there's no need to dig deep to extract them, as happens here on Earth, greatly simplifying the mining process. The NASA mission to Psyche, planned for 2022, will allow us to know more about this unique metallic world. All the resources we can extract from asteroids might be really useful for industrial purposes in the near future, once the space industry revolution has finally kicked off. Things have been changing very fast in the space industry in the last few years, thanks to the rapid growth of private space companies, the real game changers in the space industrial revolution.
I think we are entering a new era when private entities are taking a bigger role in space than they did before. They're creating a kind of more commercial market for new people to work and live in space that we didn't have before. And that's driving what I think is going to be a new era in space exploration that is less directly tied to government programs, but more commercial activity in space.
This new space industry has several main drivers. On the one hand, improvements in launch systems, sensors, and other input and innovations, such as the small-sat architecture, are driving down costs.
The new space concepts, this idea that there's this environment out there, a potential environment for economic investment and economic return that is effectively boundless. We live on a planet with limited resources. Space around us, the solar system around us, represents economic resources, mining, mineral resources that are effectively boundless.
The combination of decreased costs and increased capabilities of smallsats opens up new use cases, industries, and applications for businesses. All of these have led to the democratization of space, as it will be no longer just territory exclusive to huge national public space agencies, but also for any big or small private companies eager to invest in space.
That is what is pushing not just the governments, but the private industry and the rest of the world, not just the space-faring nations, but the rest of the world, as you're seeing now, is interested in entering this new phase of space. It will be not just for exploration, not just for gathering scientific knowledge, but to truly start using space to help us in commercial activities and economic ventures.
The key driver has undoubtedly been the increasing development of fully reusable rockets that will dramatically reduce the costs of launching. The main reason that space has been, up until now, an industry only affordable to huge space national public institutions such as NASA, ESA, Roscosmos, Russia, or JAXA, Japan. Private companies like SpaceX or Blue Origin, led by multi-billionaire entrepreneurs like Elon Musk or Jeff Bezos, are the ones that are investing most heavily in developing techniques to reduce launching costs. The development of more capable and increasingly smaller satellites is another of the drivers of this coming industrial revolution. Private companies like Planet or OneWeb are leading the production, launch, and control of these nanosats, which will radically improve our network communications, broadcasting systems, geolocation systems, or Earth observation. In addition to the aerospace industry, this space industrial revolution will also transform communications, the internet, tourism, the energy industry, manufacturing, and mining.
There's other opportunities in space entertainment and on-orbit manufacturing, things that will also create revenues and activity and create a demand for an on-orbit facility. I expect all of this to happen in the next 5 to 10 years.
The mining industry will focus especially on the moon and on asteroids as the easiest targets for obtaining resources such as minerals, metals, or water. Asteroid mining, which has belonged to the realm of science fiction until now, could become a reality in the near future. We may be witness to a 21st century gold rush.
The real estate plays when we start launching lots of people to space. It's going to be the manufacturing that we can get going on orbit. It's going to be all of the things that we can do, and you're going to need everything you can possibly imagine on Earth. We're going to need that in space. That's going to create an incredible amount of value. That's going to engage a lot of people.
There are two places in the world that concentrate most of the companies responsible for this revolution: California in the United States and Luxembourg, a very small country in the heart of Europe. Luxembourg is a very particular case. It could become the Silicon Valley of asteroid mining. This tiny state took a gamble on the space industry and nowadays hosts the SES, Société Européenne des Satellites, the world's leading satellite operator, with a fleet of about 50 satellites. This country is one of the main accelerators of this emerging space industry revolution.
Luxembourg have become very interested in asteroid mining. They're a fascinating little country, and they're a very little country. But in the 1980s, they helped to set up some of the first commercial telecommunication satellites. And now the largest telecommunication satellites in the world are from Luxembourg. So they're bigger in space than they are on the ground.
The goal of the Luxembourg government is to put into place an overall framework for the exploration and commercial use of resources from celestial bodies such as asteroids. An adventurous and unproven enterprise like space mining requires financial backing, legal frameworks, and favorable regulatory structures to allow the work to even take place. Luxembourg has expertise in this area, given its experience in the mid-1980s with the commercial satellite industry.
They're smart enough to know the financial industry, and they're a fairly concentrated economy in a couple of sectors. So they're now aggressively looking for other wins they can make. How can they get ahead of the game? And so they've realized asteroid mining, it's not just about the regulatory environment. I mean, it's easy enough for them to write favorable regulations so that it makes sense. But they also want to invest to move that forward and really cement their position in the asteroid mining industry.
Asteroid mining could become a big industry within the next decade, depending on how we solve the many technical difficulties involved. The first difficulty is to know which asteroids are the most interesting for mining purposes, as there are asteroids spread all over the solar system.
To know which asteroids to go to, we work with collaborators who have been studying meteorites and remote observation of asteroids. And from our observations, we can determine which type of asteroid it is. And the meteorites tell us kind of the range of possibilities of the mineralogy of those asteroids.
The data gathered by NASA, ESA, the European Space Agency, JAXA, the Japanese Aerospace Exploration Agency, and other space agencies in the last few years on near-Earth asteroids, the most easy accessible, will facilitate the selection of the best targets for asteroid mining companies. Another difficulty would be to decide the best way to mine, whether to bring raw asteroidal material to Earth for use or to process it on site to bring back only processed materials and perhaps produce propellant for the return trip. Or even to transport the asteroid to a safe orbit around the Moon, Earth, or to the International Space Station. This could hypothetically allow for most materials to be used and not wasted.
What makes asteroids unique and different from other bodies like moons or planets is that they are so small that their gravity is practically zero. That low gravity is good for a couple of things. That makes it easier to get to them. The energy that you need to get to them is lower than even to get to the Moon or Mars. So they are easily accessible energetically, not necessarily on time. They may be far away, but it's easy to get to them in energy. But one thing about the very low gravity of them is that all the techniques that we have learned on how to mine or extract materials here on Earth are quite different when you get to an asteroid. You no longer have that gravity that can keep an excavator on the ground and the traction that you need to move around. These things will tend to float. So you have to design different techniques how to extract this material.
At the Center for Space Resources of the Colorado School of Mines, one of the most renowned space research centers in the world, different experiments have been developed to test the specific techniques intended for asteroid mining. The scientific team uses a sophisticated vacuum chamber to recreate the extreme conditions in space more accurately.
Here at the Colorado School of Mines, we focus on creating environments in which we can test mining equipment in space, or potential mining equipment in space. We have a large vacuum chamber in which we can create a low pressure environment that's similar to what we have in space. We can place simulants of asteroid surfaces that are dusty and will create a dust cloud as we work with them. We can pull a vacuum on it to bring the pressure down to a low enough that it's simulating space. And we can do other things like chill it to very cold temperatures as you might have in space. So it mimics the conditions in space.
To recreate the conditions of an asteroid surface for asteroid mining tests with greater accuracy, scientists use simulants composed mainly of silicates such as feldspar and quartz. Most of the simulants are similar to materials we would find in carbonaceous chondrite asteroids, which are the most abundant and most closely studied. Their composition is based on a variety of data sets, including laboratory analysis of meteorites, observation of bolides, remote sensing of asteroids, data from asteroid missions, and scientific modeling. Thanks to all of this data, scientists have been able to produce the simulants with great accuracy in mineral content and particle size.
What we have here are asteroid simulants. We're making simulants of asteroids. We get the raw material for these simulants from our collaborators at the University of Central Florida, who are experts in the mineralogy of asteroids. And then we're making asteroid surfaces. We're creating a simulant of the asteroid surface. This is one example that kind of mimics a large boulder on an asteroid. These here are smaller boulders or cobbles. Friable because asteroid surfaces have rubble strewn across them, of varying sizes from boulder size to hand size to little pellets.
When it comes to developing mining techniques for asteroids, drilling and anchoring are two processes that have to be closely studied due to the peculiar properties of these small celestial bodies. In the case of drilling, the microgravity plays an important role, as the almost total lack of gravity creates different conditions for mining on Earth.
One thing to understand about asteroids is that the gravity on asteroids is very low. In a lot of processes we use for mining on Earth, we use the weight of a vehicle to hold it down so you can dig. But you can't do that on an asteroid.
The data gathered in the microgravity research in core drilling will provide conclusions on the efficiency of drilling to collect asteroid material, as well as the dangers presented by having loose debris so close to the drill operator. After collecting data on the exit patterns of the debris in a microgravity environment, an appropriate capturing device can be designed to ensure maximum collection. Developing a device that collects excess debris will also decrease the potential for damage to the drilling device.
What you can do is build systems that grip the asteroid, or harpoon it and create an anchoring point onto the asteroid. That then gives you a way to hold onto the asteroid while you use some other device to scoop up the parts of the asteroid and move it into some processing system, like cut up a metallic asteroid so that you can take in metals and refine it within some microgravity refining system. We can study the methods you might use to anchor to asteroids. Might look a little bit like a drill or a harpoon, or even just kind of gripping devices that hold onto the surface of an asteroid. And we want to study them, or want to determine ways to design anchoring equipment so that it provides enough grip so that you can then scoop and scrape and cut the surface of an asteroid.
Considering that the surfaces of many asteroids are made of boulders, pebbles, and little grains, anchoring processes could eventually be really difficult. That's why it's useful to do testing to study the best way to penetrate and anchor to that surface.
What we're basically doing is penetration testing. So what we're doing is we're taking this probe and we're pressing it down into the regolith, into this simulated regolith, because it's made from stuff here on Earth to simulate what we would find on the asteroid. And when we press it down in, we measure the forces that occur both in the upward in all different directions, as well as the torques. The reason for doing that is to kind of understand if we were to land on an asteroid and we wanted to press into the soil, say we want to anchor, or we want to extract water, or we want to build a habitat, or we even just want to understand how the surface of the asteroid is going to move or react when a meteor hits it. We use liquid nitrogen to freeze them because the surface of an asteroid could get as cold typically as 35 Kelvin. We've sealed the liquid nitrogen inside this. What it is basically, it's a probe that can move around in 6 different directions. So it has, can move in X, it can move in Y, and it can move up and down in the Z direction. An auger, so it has flutes that run around it. Those flutes allow material to travel up, so it's sort of like your typical drill bit that you would, or like a screw that would go into a piece of wood or anything like that.
This test analyzes the forces involved when drilling or anchoring on a rocky surface, which would be useful for the future asteroid mining techniques. One of these techniques is surface mining. On some types of asteroids, material may be scraped off the surface using a scoop or auger, or for larger pieces, an active grab. There is strong evidence that many asteroids consist of rubble piles, making this approach possible. Another technique is shaft mining. A mine can be dug into the asteroid and the material extracted through the shaft. This requires precise knowledge to engineer accuracy of astrolocation under the surface regolith and a transportation system to carry the desired ore to the processing facility. The magnetic rake is one intended for metal asteroids. Asteroids with a high metal content may be covered in loose grains that can be gathered by means of a magnet. The question now is whether asteroid mining nowadays is really a feasible industry if we think of it as a mining industry that provides resources for the Earth.
The cost of sending a spacecraft to the asteroid belt used to be about the same as if the spacecraft were made of pure platinum. So it didn't seem to make sense to go out and get diluted platinum from something that cost you so much to send out there.
Nowadays, the most viable option is to mine and process the resources in situ. As with our present technology, the cost of sending a spacecraft and returning it fully loaded back to Earth would be extremely high.
What is more attractive is to use the resources from that asteroid to use it in space. That makes it more economically feasible because bringing it from Earth is extremely expensive. Bringing water from Earth, bringing the iron and the nickel from Earth is very expensive. So then it becomes economically feasible to extract the resources from the asteroid.
Maybe in the future, if we are able to radically reduce the cost of space missions, it could become feasible.
In the asteroid belt, there are orders of magnitude more materials out there than we've ever imagined. So what you have is companies that can get very excited about claiming these future sources of mineral wealth that will eventually become starships and space colonies.
That dream of space colonies on asteroids might not be so far in the future. We now know that there are asteroids made almost entirely of metal that could potentially become an almost endless resource for industries on Earth in the future.
The existence of platinum group metals was probably the very first resource that attracted interest from companies to go and extract those metals from asteroids. Because of their high value on Earth, there's plenty of platinum on those asteroids. In fact, it has been said that an asteroid a couple of kilometers in diameter or in size has more platinum than has ever been mined and probably will be mined in the next 50 years on Earth. The problem again is it economically feasible to go after that platinum? Is extracting the platinum from Earth more expensive than on asteroids? Not at this moment. The amount of money that you need to launch a rocket to get there, to extract the platinum at this point is not competitive. But again, at some point, it may become so hard to obtain the platinum from Earth that it will make sense to actually go to an asteroid to do that. The other thing to consider is the moment you start bringing those large amounts of platinum to Earth, the price of the platinum will just collapse immediately. All of a sudden, you will have all this metal available that it changes completely the price that we put on this. Obviously, if there's more demand for it, if now that we have more and we can use it in many more applications, then it will make it much more attractive to go after it.
This emerging industry is about to kick off. Undoubtedly, the key game changers are asteroid mining companies that are investing mainly in the development of technologies to make this industry economically feasible. Among the asteroid mining companies, there were two that led the race until recently: Deep Space Industries and Planetary Resources. However, due to the low feasibility of the mineral extraction, they are now in a redefining process. In addition to those, there are other asteroid mining companies, each focusing on specific aspects of this industry, such as the production of propellant from water located in the asteroids, the development of robotics, or the search for the right targets. One of them is TransAstra.
TransAstra has a business plan that's focused on extracting rocket propellant from asteroids. You could call that asteroid mining if you want. And then using that rocket propellant to fill refueling stations in space, to refuel NASA spacecraft and private sector spacecraft. For NASA, it would be refueling spacecraft that are taking astronauts on a mission of exploration. For private sector, we can refuel space tugs that deliver satellites to their destination orbits.
TransAstra is a new kind of aerospace company intended to contribute to the development of the concept of the transcontinental railroad of space. Their vision is for humanity to become a spacefaring species homesteading the solar system.
We can build the transportation network. It's kind of like the transcontinental railroad of space that will make it possible for industries to go in space for a profit.
Their ultimate goal is to turn thousands of asteroids into refueling stations for NASA and commercial spacecraft, opening the frontier for NASA human exploration and commercial industries beyond imaging satellites and telecommunications. They aim to lead the work in supplying services for 21st century industries of asteroid mining, space solar power, space tourism, and manufacturing in space.
That is going to create the greatest industrial revolution in the history of mankind. And we're standing right here at the moment in history when it's about to happen.
The company has a clever mining technique called optical mining that benefits from the solar power to mine the water on asteroids, water to be used as propellant.
One of the best energy sources we have in space is the sun, and that's one way we can use that is by building reflectors that concentrate sunlight to extract and process materials in space. An example of this is a technique called optical mining that is invented by TransAstra and Joel Sercel. We are collaborating with TransAstra to help understand the basic process of concentrated solar interaction with minerals of C-type asteroids.
TransAstra has invented a process that we call optical mining. Optical mining is an approach whereby highly concentrated sunlight is focused onto the surface of an asteroid or other volatile containing body. The highly concentrated sunlight heats and thermally fractures, means it breaks up the surface. So you have the surface of the asteroid or other water-containing extraterrestrial body. The highly concentrated light hits the surface, and as it heats the surface, it fractures it due to the heat. What's really exciting is that the little particles of the broken surface then individually heat up very fast. And all you have to do to get the water and other valuable compounds out of the asteroid is heat it up. The water comes out as vapor. That vapor actually cleans the surface and exposes the next layer of surface and for the sunlight beam to fracture, and it's a continuous process.
The optical mining technique has been tested in vacuum chambers at the Center for Space Resources of the Colorado School of Mines. They use hydrated mineral type simulant, similar to the material found on the surface of an asteroid.
I have the chamber itself, and that makes it a vacuum and allows me to put in samples and make them hot or cold, depending on the kind of test that we're doing. Then I have a lamp on top of it, and that allows me to have sunlight focused down, or simulated sunlight focused down onto my sample. And then inside the chamber, I have samples of many different kinds. We will get the light out using just sunlight. So we'll concentrate it down to a spot, and a column of water vapor will rise from the surface. So this will probably be the first technique that people use when they're gathering space resources. So after the ice on top of the regolith turns into steam and is sublimated, and it's going to form a little cloud, we're going to take a tent and put it on top of this cloud. The tent is going to be colder than the ground underneath, and in this situation, whenever something is the coldest, that's where the ice will stick.
TransAstra is developing an innovative mission concept called APIS, an acronym for Asteroid Provided In Situ Supplies, that includes an autonomous spaceship that will be launched on spacecrafts to reach asteroids.
So what we're going to do is we're going to build a spacecraft that's about the size of a pickup truck and launch it out to an asteroid that's about the size of a house. And then this spacecraft that's about the size of a pickup truck will have inflatable structures, and it'll have a bag that it uses to inflate and then enclose the asteroid. And then the solar concentrators will pump sunlight in, and then through the optical mining process, we'll excavate the asteroid, extract the water, and freeze the water in ice bags. So this honeybee mission, as we call it, will take about 6 months to get to the asteroid. It'll do mining for about 3 months, and then it'll take 6 months to get home, and it will bring back 100 tons of ice. And that's the first small industrial scale mission to bring back an economically important quantity of rocket propellant that can change the economics of space. And we think that that will launch a gold rush in space to harvest asteroid material and also material from the lunar poles. And that will make it so inexpensive to operate in space that it will become practical to do things like build solar power stations in space where the sunlight is much more accessible, much more consistent, much more cost effective if you can launch into space inexpensively enough.
When it comes to benefiting from asteroid resources, one of the greatest challenges is knowing which are the best targets among the thousands of asteroids floating in space. Aten Engineering is a company focused on that field. Their goals are to develop technical solutions for the detection, discovery, follow-up, and characterization of near-Earth asteroids.
We're still working to find some of these bodies with our telescopic surveys, and it may actually take a next generation of telescopic surveys, or possibly a space-based telescope specifically designed to find these kinds of objects.
Up to date, more than 10,000 near-Earth asteroids have been discovered. It's not an easy task to find and to follow them up. But thanks to the Minor Planet Center data and tools, Aten Engineering has been able to study and track those objects. The biggest challenge is to characterize them in terms of size, rotation periods, and spectral composition. Until now, less than 10% have been well characterized. It's estimated that with present technology, it will take about a century to study the entire known population.
We use telescopes to look at the spectra of asteroids, and in the spectral signature you can see different things that tell you what it might be. So you can determine if it's a metallic asteroid, or a stony asteroid, or a carbonaceous.
They are now focused on developing accessible technology for characterization to keep pace with discovery. They are working on quick visible spectroscopy and fast cadence light curves that could be obtained with a telescope in just a few days, as well as in long arc astrometry to be used for phase curves that should take months. All of these would undoubtedly accelerate the rate of characterization of near-Earth asteroids, which would help to analyze their potential as resources for mining purposes.
I'm really excited about asteroids, the near-Earth asteroids in particular, as targets for future human and robotic exploration.
Other companies like Off-World are focused not on the study of the asteroid's properties, but on the development of robotic devices to mine autonomously. Their ultimate goal is to create a squad of autonomous robots working under human supervision on other planets and asteroids, which will allow human beings to spread beyond Earth.
While these little asteroids offer us a lot of benefits to go to as targets, there are still a lot of challenges involved with going to a little asteroid like that.
The environment out there is extremely harsh. Human settlers will have to cope with long, deep space journeys, lethal cosmic radiation, zero or lower gravity, or artificial atmosphere. Off-World thinks the best way to minimize the risks of establishing a permanent and sustainable settlement on other planets would be to have a local robotic army that would be in charge of the hard work. Building landing pads, excavating underground habitats, extracting water ice and materials, making drinkable water, breathable air and rocket propellant, manufacturing basic structures and solar cells, producing electricity, and eventually replicating themselves. As the asteroid mining industry grows, thousands of mining robots would be needed everywhere. These robots should be small and robust enough to survive launches on rockets, solar electric powered. Extremely adaptable to work in a wide range of environments on asteroids, the Moon, or Mars without a major redesign. Autonomous and fast learning to survive without on-site human supervision. And modular and reconfigurable to maximize the reuse of launched hardware. The robots should also have self-replication capability using local resources and should be able to manufacture the first off-world computer chips, closing then the robotic self-replication loop. All these asteroid mining companies are now leading a race that could push human beings beyond their natural frontiers to colonize these small, mysterious, rocky worlds in the near future. The potential colonization of asteroids is not an easy task at all, as they are very harsh environments for us, without any shielding from cosmic radiation, as they have no atmospheres or magnetospheres, with extremely low gravity and with a very high chance of collision with other celestial objects. The two main reasons that justify moving off Earth to asteroids would be to benefit from their almost unlimited resources, as well as their colonization as a risk mitigation strategy to ensure the long-term survival of our civilization in case of a planetary catastrophe.
We really want to get the asteroids that are closest to Earth's orbit. There's enough material in those near-Earth asteroids to support maybe 100 billion people living in Earth orbit. There's 1 million times more material in the main asteroid belt. So after we've got people to orbit, we're using this material to live and work and build cities, we can expand to a huge civilization circling the sun. That's pretty exciting.
You're looking for stuff that you want, and specifically, if you're going to turn an asteroid into a place for people to live, you want the kinds of things that would support life. Like especially you would want a certain amount of water. You would want components that you could turn into soil for a greenhouse so that you could grow your own food. You would want sufficient metal concentrations that you could make your own building materials from the base metals. You would want enough precious metals that you could export precious metals to sort of feed yourself and have things to trade with other asteroid colonists or with the moon people or the Earth people or whatever.
Throughout our history, opening new frontiers as thrilled generations of explorers and pioneers. Asteroids could be considered the next frontier. The fact that asteroids are small rocks floating in space offers several advantages, but also some disadvantages. Their extremely low gravity, because of their small size, is one of the greatest advantages. This low gravity would make construction of huge structures much easier and would reduce the costs of landing and launching rockets in comparison to the Moon's or Mars's higher gravity wells.
The gravity is so low on these little objects that it's more akin to to going and docking with the International Space Station or rendezvousing with something like the Hubble Space Telescope. So you're not going to be walking on these objects, you're going to be floating near them. And it makes, in some aspects, it makes that portion of doing a mission to one of these objects a lot easier.
Another pro would be the large number of possible sites because of their numbers, with over 300,000 asteroids identified to date, as well as their variety in chemical composition, with carbon-rich, metallic, and stony asteroids.
There are metallic elements and water in the surfaces of those little asteroids that are great resources for us out there in space once we have a thriving working economy out there. If you want to make rocket fuel to power your spacecraft that are moving around the inner solar system, it's a lot easier to make that fuel from the material on a little object with very little gravity than to have to haul it off the Earth all the time and lift it out of this deep gravity well. So the asteroids have great benefits for us, exploration and science and resources. I think they're wonderful destinations.
However, to make this future mining industry a reality, we need to solve several challenges such as asteroids' low gravity and zero atmosphere, which make them vulnerable to cosmic radiation and to the impact of small objects.
We've never actually had any experience in human spaceflight of working in a very low gravity environment that's very geologically dirty. Unlike on the Moon, where if you stir up dirt, it very rapidly settles again, on a little asteroid, if you stir up the dirt in that environment, it's going to stay around you in orbit around that asteroid for the entire rest of the duration of your mission. It's going to contaminate your spacecraft, it's going to contaminate your suit, it's going to make the visibility environment difficult. So there are challenges like that. Combining the challenges of a zero gravity EVA, a spacewalk, with the dirty environment of something like the Moon is something we have no experience with. And that's going to be, I think, one of the biggest challenges in human crews working around these little objects.
In a not-so-distant future, asteroids may become our new industrial target, a place to mine to benefit from their resources, used not just on Earth, but especially in space.
We can build the infrastructure that moves industry in space, not in 20 or 50 or 100 years, but starting in 3 or 4 or 5 years. And we can be harvesting rocket propellant in less than 10 years and building the transcontinental railroad to the solar system.
They might also become pit stops on the long journeys to Mars, and who knows, to our new home as well.
That is where the value of asteroids really lie, as they become gas stations or pit stops or stepping stones in our process to explore further and further into the solar system.
We are about to go one step further in the conquest of space, as the asteroids could soon become our next frontier.